This is the operational amplifier. This one is the actual diagram. It is multi-stage, shown the 3 stages. The input stage is differential amplifier, then there are more stages to amplify the signal, and last stage is push-pull amplifier. There are into inputs and there are other 2 outputs. Okay. Generally the output is taken at one terminal and the second terminal is oftenly grounded. This is a symbol of the operational amplifier symbolic diagram. This is shown by a triangle. There are the 2 input terminal V1 and V2, and there's one output terminal V out, and plus V plus 15 volt minus V equals to minus 15 volt. They're the 2 supply. Not necessarily they are the 15, maybe 12, maybe 18, like that. And 2 inputs V1 and V2. The inverting input implies that if we give any type of signal at here, we get an output signal out of phase. Any type of signal applied here, applied to V2, we will get the output opposite in phase, while as any type of signal which is applied to the terminal here V1, we will get the amplified output and exactly of the same phase, same shape, same phase, no phase difference. So that's why the V1 is called non-inverting input. We will get an output amplified and no phase reversal. But any type of signal which is given to V2, that will be inverted at the output sides. That's why it is called the inverted output. There are some important points. An operational amplifier is a multi-stage amplifier. The input stage of an op amplifier is a differential amplifier stage. So its input of the op is a differential amplifier, like shown here. An inverting input and a non-inverting input. There are 2 inputs. One is inverting, second is non-inverting. The inverting, it is assigned by minus, non-inverting assigned by plus sign. It is having very, very high input impedance, usually assumed infinity for ideal at both the inputs. At here and at here, the inputs, they are having infinite impedance, and output impedance were very low, less than 200 ohm. Here it is ohm. A large open loop voltage gain, typically 10 to the power 5 for real, and for ideal it is infinity. And very large common mode rejection ratio. The voltage gain remains constant over wide frequency range, mean having very large bandwidth, and very large CMRR, common mode rejection ratio. This is a symbolic diagram of the op amplifier, but oftenly the power supply, here they shown the power supply, plus V 15 volt and minus V minus 15 volt, but oftenly they are omitted. The power supply omitted. There's simply the further symbolic diagram of the op, only 2 inputs, plus that is non-inverting, minus it means inverting, 1 and 2 and an output. Here the power supply connections are omitted. Okay. The output voltage means the gain actually. Output voltage, because we are giving input to the op and we are getting an output. The output depends upon what's the voltage gain of the op amplifier and the polarity relationship between the V1 and V2. What type of, whether V1 and V2, they are differential signals or the other common mode signals like that, mean their polarities, and the value of the supply voltage, how much the supply is given to the op amplifier. So output voltage depends upon all the three. This op amplifier is called open loop op. Open loop means that the output, there is no feedback. Output is not connected to the input sides through resistance. So this is called open loop op amplifier. This op is called closed loop because here the output is connected to the input V2 through resistance RF. So this is called closed loop op amplifier. There is a feedback, and this feedback is actually a negative feedback. So this is called closed loop, giving a negative feedback. Output is connected to input through RF. When the operational amplifier, it is open loop, okay, then it is having maximum gain, and that is written with AOL. AOL mean open loop, and open loop, the real amplifier having gain that is greater than 10,000. Okay, the term open loop indicates a circuit conditions when there is no feedback path, that output is not connected to the input. Op amplifier almost operated, practically op amplifier is always used in closed loop when the part of the output signal is fed back to the input side. There's negative feedback. This is practically used like this, but here the gain becomes low, basic negative point of the op, but it is having many advantages, many applications. Many applications are related to the closed loop op amplifier. What is gain of the op amplifier is reduced when it is it is used as a closed path. So then the closed path gain is represented as ACL. Closed loop voltage gain is represented by ACL, closed loop gain. The supply voltage for an op amplifier are normally equal in magnitude and opposite in sign. Like for an op it may be plus minus 15 volt, and for second op it may be plus minus 10 volt. There are two supplies, one positive and one negative. Suppose an op amplifier has supply plus minus 10 volt and open loop voltage gain is 20,000. Let us find the differential voltage V in to avoid saturation. V saturation equals to V supply. The saturation voltage, maximum voltage, which is given by the op. The maximum voltage the op amplifier which gives us, it depends upon the supply. If the supply is of 10 volt, it will give maximum 10 volt and nothing more than that. And in that case, like if it is having the 20,000 gain, and what should be the input signal, maximum input signal which can be amplified, it is 10 volt 20 divided by 20,000, that it is 0.5 milli. Therefore the input voltage is 10 volt divided by 20,000, that is 0.5 millivolt. So this is maximum input voltage which can be amplified by the operational amplifier. And if the input voltage increases to this value, even then the op amplifier gives 10 volt, not more than that. Okay, if you are supplying the input signal like 1 volt, 2 volt, 5 volt, even then it gives the 10 volt only, maximum 10. Okay, if the input is less than 0.5, then it will be amplified using this gain 20,000. If it is 0.5 or greater, then the op amplifier will go to its saturation. Like shown here, if you are increasing the input, okay, up to this value, the output increases linearly, and the gain is effective. But if the input is here, if we come to this input value or more than that, the output becomes constant, which is equals to VCC. The output, the further output will not increase. The output will reach to its saturation value. Similarly to the negative sides, for the negative supply, the output increases up to this value. If for further increasing the input, there is no uses, there is no useful, the output remain constant. If the input further increases from to this value, if it increases, the output remain constant. Okay, so only there is a linear relation between input and output for the small up to small inputs, because this op is gain is too much, so is amplifies, but just very soon it reaches to the saturation, like here saturation or here saturation. Okay, so if the differential input voltage equals or exceeds 0.5, what happens? It will driven into the saturation and device will become non-linear. Now here it is the non-linear. Here this is a linear region. Okay, to this side is a negative saturation, to this side is a positive saturation. Although the input terminals of the op amplifier are labeled as plus and minus, there are two inputs, non-inverting and inverting, but it doesn't mean that we have to apply positive voltage to the plus terminal and negative voltage to the minus terminal. It's nothing like that. Any voltage can be applied to either terminal. Positive and negatives are the relative terms, that if plus 4 is applied at the positive terminal and 2 volt plus 4 volt is applied at the positive terminal and plus 2 volt is applied to negative terminal, then positive terminal is at more positive potential with respect to the negative terminal. Therefore, the output voltage will swing towards the positive V of the DC supply, mean plus VCC of the DC supply. The output voltage depends which voltage is greater. Okay. This is an ideal op amplifier having two inputs, and the resistance between the two inputs, they are the open circuit. Open circuit mean input impedance is infinity. Z mean impedance. Input impedance is infinity between the two. And here this is voltage which is amplified by the op, that it is A times the input voltage, and here no resistance is shown, like output resistance is 0 for the ideal op amplifier. The ideal op amplifier having Z out equals to 0, as well as is having the gain equals to infinity, ideal. But in case of real, there are the two inputs, and between the inputs there are input impedance Z in, as well as that input impedance too high, no problem, it's very high, and there is an output impedance Z out, that's very low, as well as AV is not infinity in this case, although it is very high, and we are getting an output at here. This is a practical op, this ideal op. This one is practical, this one is ideal. AV infinity, Z out 0, Z in infinity. There is Z in very high, Z out very low, and AV is very high. As the voltage gain of the op is very high, so extremely small input voltage will produce a large output voltage. Input impedance very high mean the op amplifier will not draw any current, or will draw very very small input current. Okay, if it is ideal, and then it will draw zero current. If it is real, then it will draw very small in. Output impedance of a practical op amplifier is very low. It means that the output voltage is practically independent of the value of the load connected to the op. Mean whatever the load is connected, whatever the load resistance is, whatever the appliance is connected at the output side, the voltage remains constant. Output voltage will not vary. It will not vary. The output voltage will not. It remain constant. Whatever the load connected, whatever the appliance is connected at the output of the op amplifier, if it is good if the output impedance is very low. Okay. Characteristics of an ideal op amplifier: infinite voltage gain, infinite input impedance, and zero output impedance. Okay. The voltage gain of ideal op amplifier is infinite. It means we can set even V and V input approximately equals to zero. That means two small voltages can be amplified. Input impedance infinity means ideal op amplifier has zero input current. It will not draw any input current. Output impedance is zero. It implies that the output voltage does not depend at all on the value of the load connected. Now the bandwidth of the op amp, bandwidth means the frequencies. Generally amplifier works only over a limited range of frequencies. The range of frequencies over which it work properly. The range of frequencies called the bandwidth. Op amplifier, no problem having a large bandwidth, it depends upon the closed loop gain of the op amplifier circuit. So we define the gain bandwidth product. That's a multiplication of the gain multiplied by the frequency f2. Here it should be f2 minus f1, because f1 is taken as 0 here, because op amplifier works on a DC supply also. DC means no frequency. So it is defined as closed loop gain into f2, and if the closed loop gain is 1, if it is set as 1 closed loop gain, then gain bandwidth product then becomes, if ACL is 1 unit, then it becomes simply f2 then written as f unity. F unity means when ACL equals to 1, closed loop gain when it is 1. So that frequency is called f unity. So gain bandwidth product, it is important because this factor is constant for a given op amplifier. Mean if the closed loop gain is low, the f2 will be high, the maximum frequency at which the op amplifier gives a good response. So if it is low, this will be high. If this is high, then f2 will be low. So but the product remain constant. It can be proved that gain bandwidth product of op amplifier is constant. Op amplifier is capable of operating as a DC amplifier also. So bandwidth is f2 minus f1. F1 is 0, mean for the DC having no frequency. So it starts from the 0. Lower limit is 0, upper limit is f2. The slew rate. The slew rate of the op amplifier is a measure of how fast the output voltage can change. How fast the output voltage can change, and it is measured in volts per microseconds or milliseconds. If the slew rate of op amplifier is 0.5 volts per microsecond, it means that the output from the amplifier can change by 0.5 volt for every 1 microsecond. This is a maximum voltage which will change 0.5 volt for 1 microsecond. The slew rate of an op amplifier or any amplifier circuit is the rate of change in the output voltage caused by a step change in the output. And what we mean by that? So let's try to understand what we mean by actually the slew rate. No problem. The definition is the voltage can it is measures how the fast the output voltage can change. Okay, but what the actual mean is of the slew rate, let's see. Like this is a rate, it's a step voltage. The input is going from low to high within no time actually. Like instantly it is going from low to high. But at the output size cannot follow this thing. So output takes some time to reach to the maximum value. So output takes, this much time. It takes more time to reach the maximum value. So again, when the input is coming down instantly, but the output again takes some time for coming down from high to the low level, it takes some time. So output is slightly distorted from the input because of the, this slew. Okay. A typical general purpose device may have a slew rate of 8 volts per microseconds. This means that with a large step change is placed on the input, the device would be able to provide an output of 8 volt change in 1 microseconds. So, slew rate, it should be greater. If it is greater, then it is good, because in a lesser time, more voltage can be handled by the op. So otherwise there will be distortion, that is called the slewing distortion. So if the op amplifier is operated above the slew rate limit, the signal will become distorted. Like this is the input signal which is given to op. Then if the op is not good, if it is having very low value of the slew rate, then the output may be distorted like this. The input is like this. This is input and output is like this. So output is distorted. The slewed waveform which is distorted. So a sine wave with a frequency f hertz and a peak value of V volt required op amplifier with a slew rate. There is a formula of the slew rate, and where we have to fill the value of we have to substituting the value, to substitute here the value of f and the value of the peak voltage. Okay, then we will get the slew rate 2 pi fv volts per second. This is required to ensure this value, this slew rate is required. This is required to ensure the maximum slew rate requirement which occur at the zero crossing point can be met. So this is a zero crossing point. Okay, maximum rate of change is here. So this is the formula for calculating the slew rate. To give the distortion free operation, the slew rate of the amplifier, it is calculated. This is a formula 2 pi fv. Okay, and f is the highest frequency which may be applied to the op, and the slew rate is measured in volts per microseconds generally, and V is the peak voltage. For example, the op is required to amplify a signal. Peak amplitude is 5 volt and frequency is 25 kilohertz. This is the maximum frequency which is applied to op. Then there should be a slew rate. The slew rate should be 0.785 volt per microsecond. This is required. Okay, this is a required slew rate. If it is less, if slew rate is less than this value, then the signal will be distorted. Then there will be the distortion. This is the meaning of the slew rate.